Hi, in this video what we're going to talk about is simple harmonic motion, otherwise known as oscillations. So systems that oscillate are going to include spring systems and pendulums. As you can kind of see with these crazy little GIFs here, is that oscillations occur when you have periodic motion, so things that return back to where they started. So because they have this periodic motion, they're going to have some conditions. So we can analyze those conditions and make predictions as always in physics. So studying systems like pendulums and springs are very relatable to real life situations. So for example, although we're looking at springs here, a lot of atomic behavior behaves like springs. So when you look at the molecular level of surfaces, they're actually going to have oscillations very much like springs, so it's very important. So if you study the Bohr model of the atom, you started these things called harmonic motion and harmonic oscillations, because at the quantum level, waves start to behave like particles or vice versa, and we can relate some of these systems. And pendulums are another good thing to study because although the simple idea of pendulums, which we're going to talk about, is something that swing back and forth, there's lots of relationships that can be studied. A silly one is, being on a swing. So being on a swing is like a pendulum. Another way that people study pendulums is inverted pendulums, like trees. So instead, you have the tree up like this and the mast on the top, and things will oscillate back and forth that way. So studying these systems are very important for not only physics, but for real-life applications. So in the first video, I'm probably just going to get to just describing a little bit about our oscillators. So talking about their conditions, what makes them simple harmonic motion, and some of the initial conditions of springs. So what I'm going to do in this video is talk about and calculate the following features: the frequency, period, acceleration, force, and the strength of the spring, known as the K constant. So when it comes to looking at a spring, the video before is exactly the same as this, but you can see that it's a periodic motion. And notice if you follow the green dot here, it actually follows the same green dot here. So there's a relationship between an object moving up and down and an object moving in a circle. They're periodic. Although we're not going to talk about the real space and phase space, but you can kind of see the parallels of an object technically going up and down as it goes in a spring system. So you can try this out by clicking this animation. You'll see the same connection that I made before. So things that oscillate are periodic, even though it's going up and down / in a circle. So what is a simple harmonic motion? So the word simple comes from a really silly concept, as you might imagine, simple systems. So by simple systems, we're only going to have one mass on a spring here. It's going to be an ideal spring, so the force will be, not constant, but the force, the system doesn't change over time. And for pendulums, we're not going to have ones that are drastic, the ones that go all the way up. We're just going to have some small angles. Since they're small angles, we call them simple. Harmonic refers to the idea that these things are periodic. So there are actually two conditions that exemplify the simple harmonic motion. Now the first condition I'll talk about is periodic. So we saw already that a spring will oscillate up and down like this, creating what we call periodic. However, if you look at something like a pendulum, you get the other case where it goes back and forth. So because it returns back to where it started, and it's symmetric, meaning that, from the equilibrium position back to its rest position is the same, we call it periodic. Restoring force. So what happens with restoring force is that in order to return back to its original position, there's got to be a force to do that. So as an example, so springs, if you notice, if you pull down a spring, actually I can even show you. Let me show you. So if you look at these springs right here, and I hang it on here, so notice that dotted line represents, well actually let me just hang this here, and I want it right at the equilibrium, so like that. So I'm going to put this dotted line here. So I think through personal experience, you know that if you pull a spring down, and I'm holding this down right now with my mouse, that it's going to want to spring back up. And if I let go, there's the case. And then of course the extreme case, if I compress it, it's going to be pushed down like that. So when I talk about restoring force, I mean it's the force generated to go back to this dotted line right here. So notice the condition for simple harmonic motion is the larger the distance, the more restoring force, as you might imagine. The further I pull this back, the more force that this is going to exert to go back to the rest position. So that is for springs. And then for pendulums, see if I could do this really quick. I didn't think I'd get to pendulums, so that's why I didn't set this up right away. But I should be able to do it real quick. There we go. Same thing. So this dotted line represents what we call the equilibrium position, the position at which it wants to be at rest. And naturally, as I pull this back, it's going to, let me just pause it at the top there. So if you see the acceleration right here, you'll see that it gets bigger the further away. That's the restoring force. Now, I know I said acceleration, but the net acceleration is always proportional to the net force. So even though this is A, this is also another way to look at the the force of the system. So the condition for simple harmonic motion means the further back you make your distance, the more restoring force. And you can see that here. So, for example, something that's not simple harmonic but might look like simple harmonic is like a rubber ball when it bounces up and down. So as it bounces up and down, it's periodic, but notice that the distance it covers is not the same. It's not symmetric, so it's not going to be simple harmonic. Or another obvious case, I know this is going to be silly, but an object moving in a straight line is not simple harmonic. And that's because it's not periodic, or you don't have this restoring force. So another random example of simple harmonic, let me go back here. And move this over here. I know this is going to be silly just so you can see this right here. So actually, I'm just going to skip back to this. So simple, for your cases for physics, you're just going to need to know that simple harmonic motion are simple pendulums and simple springs. That's the biggest thing you need to know about this. Restoring force points back to the equilibrium position. So I demonstrate that with the pendulum right here, and although we didn't have a force arrow, you'll notice that it will do the same thing. In fact, we might be able to see it. Let's see if we can. So let's go to this. Do they show? No, they don't show that. Okay, I just wanted to see if they would. Now, when it comes to the pendulum systems, we have small angle approximations. So the net force that's created when we saw that arrow in the pendulum system is based on some trigonometry, which I'm not going to derive, but in the end it comes out with a sine case. So we say that simple pendulums occur at small angles, so less than 15 degrees. So the big pendulums are not simple harmonic because their mechanisms change. Don't worry, I won't change this other than 15 degrees or less. Move this back. Okay. So since these things are periodic, just like we've measured before, this is a review, but these are going to have measurement features of time, so such as period. Period's time to complete one cycle, which is measured in seconds, and then the frequency is how often that occurs, so the number of cycles per time, so that's going to be measured in hertz. So I'll just briefly talk about this. So when you're, I can do it, that's okay. So when you're finding the period of a spring system, as you might imagine, so let's go ahead and let's displace it by 10 centimeters. So I'm going to displace it to the 40 mark right here. I'll let it oscillate. Now the program's nice because I could do that, right? So let's do 1/4 time. The period is the time it takes to make one full cycle. So you can start anywhere. So I'm going to start at the bottom here because it's easy to measure. So I'll start the stopwatch right at the bottom and pause right at the bottom there. So 54, it's not 54 seconds, it's 0.54 seconds, sorry. So that's the period of our system right there. As always, you can calculate these values if you know one or the other by taking the inverse of the two. Okay, so some things that I need to talk about is we can, although this is, a mass oscillating up and down, we can describe it like a sine wave since it is periodic. Although it's not moving in the x direction, we spread it out so we can see it easier. So if you look at this, the y direction, the spring will move up and then cross the equilibrium position and move down. So this line is called the equilibrium line right here. Now, the furthest that spring moves is called the amplitude, labeled by a capital A, and you'll see this in our calculations. So that's how far the spring goes back. Unless otherwise spoken, we usually refer to the maximum. So this is the furthest that it goes back, the amplitude right there. Now, the period, if this is the time axis right here, will tell us how long it takes to make a full cycle. So notice a full cycle is defined as the time it goes up and down back to here. So notice this line right here. That's the period. A lot of people will say it goes down and comes back. Now you're right, it does come back, but that's only half of the motion because it does technically go below that as well. So you need to take both the up and the down to measure the period there as capital T. So we can do two types of spring systems. We have the vertical spring system, the horizontal spring system. So when we deal with the vertical spring system, the horizontal line, so let me take a step back. So if you look at the spring before we put a mass on it, it's going to look like this. So then all of a sudden we're going to put the spring on it, the mass on it, and it's going to stretch that spring. So what we do is after you put the mass on it, we draw the equilibrium line right here and take our measurements from here. So when it comes to compression and stretching, we always take it from the equilibrium line like this. So when we do these problems, we usually take it from the center of mass, which is about right here. So wait until you let it hang and rest to draw the line. And then for these, what we do is we draw a line at rest. So both of these conditions are at rest. And this is going to be the equilibrium line, the line that I talked about in the previous slide, where it's at rest. And then this thing's going to go this way, and then this thing's going to come back this way, etc., like that. And then just a note on the amplitude. The amplitude would be from the equilibrium line to the furthest point, like this. So usually we take the absolute value of amplitude, but yes, technically this is negative, but the value should be the same because our systems will be equilibrium. And same thing, if you pull this back to here, that would be the amplitude, like that. And then, of course, I'm getting cut off right here, but you get the idea. The amplitudes are measured like this. And that's exactly what I'm talking about in this slide. So unstretched and the stationary conditions for the equilibrium line. Now it's important to establish where that is so you can take your measurements. So I'm just going to introduce this and continue in the next video and talk about this. But what we can do is we can actually find the period of the mass spring system without using a stopwatch, which is actually kind of convenient because not all the time can you watch the spring system. Sometimes you need to just do your calculations just by the conditions of the spring. So the period of our spring system is going to be based on how big your mass is and how strong your spring is. And as you might imagine, it's going to go longer if you have a bigger mass because it's going to be heavier, right? It's going to take longer to do that. And the stronger your spring, it's going to speed up because it's really strong. So as soon as you pull it back, it's going to go right back to its original position. So K, if this is large, makes this number small. So bigger K constant gives you a smaller period. A bigger mass gives you a longer period. Now the interesting part is it doesn't matter about the amplitude, how much you pull back. It just matters about the conditions of the mass and the spring of your system, which is pretty neat. In the next video, I'll show you that this is actually true.